Electronic Circuits, lecture number 10. And we will continue our discussion on high frequency response of BJT amplifier. So last time we have seen the origin of inter-electrode or parasitic capacitance in the form of C mu, C pi, and CCS. And also we have additionally seen the effect of, what was the origin of the wiring capacitances. So CWI and CWO were the wiring capacitances. So here we have written over here, this is my BJT amplifier, common emitter configuration, wherein I have a small AC signal and it's getting amplified at the output. I am powering my BJT with a DC voltage, and this is the voltage divider network configuration, biasing circuit. Now for this circuit, I'm just revising what we have covered last time. Capacitor CC1, CC2, and capacitor CE are externally connected capacitors whose ranges are in microfarad. Capacitors C mu, C pi, CCS, CWI, and CWO are called as inter-electrode, and CWI and CWO are called as wiring capacitances. Together they are called as parasitic or stray capacitances. And all of them have a range in the, all of their values are in the range of picofarad. And these capacitances are inherent due to the structure or due to the wiring in the in the circuit, right? So along with the BJT, these capacitances come along. Now, why does capacitors only affect the high frequency? Well, we will discuss that shortly now. And next, we have seen a concept of Miller theorem. So what does the Miller theorem says? Whenever we have a feedback capacitor connected between the input and the output of an amplifier, of an inverting amplifier, then that capacitor can be splitted into two parts, one at the input side and one at the output side. So CMI is the Miller input capacitance and CMO is the Miller output capacitance. And we have seen the derivation. I have said the recorded video of the derivation. CMI can be written as 1 minus AV into CF, where CF is the, the feedback capacitor, and AV is the voltage gain which of an inverting amplifier. So voltage gain is negative. CMO is 1 minus 1 upon AV into CF. Okay, so these were the formulas for the input and output Miller capacitance. So this was an important concept which we'll be utilizing right now. And yeah, so for today's and this we have discussed that why does the gain of the amplifier fall at low frequency and why does the gain of the amplifier fall at high frequency. So we'll see that today, that how does the gain of the amplifier actually is affected by this externally connected capacitors and internally present parasitic capacitances. Now, for this part, we are determining the high frequency response, right? So for high frequency, connected capacitors CC1, CC2, and CE are behaving as short circuit, and all the stray and the parasitic capacitances will remain in the circuit. Now, why is this possible? Let me show you in a document. I've already said this in the form of analog electronic circuits, lecture number 9, extra part 2. The recorded video is with you all. So here I have shown that status of all the capacitors in different frequency range. So at DC, all the capacitors are open, including connected and stray. For low frequencies, as you can see over here, for low frequencies, the connected capacitors are considered, whereas the stray capacitors are open because the impedance value is very, very high, and impedance is very, very low for connected capacitors, and it's very high for stray capacitors. At mid frequency, the connected capacitors are short circuited. At mid frequency, you all can check out with a number. Here the impedance is very, very low. That's why they are short circuited. Whereas the stray or the parasitic capacitances are open because the impedance XC is still very, very high. Next, we saw at higher frequencies, the impedance offered by the capacitance, that is the connected capacitance, is very, very low, right? It's in the order of 10 raised to minus 3 ohms. So that's why connected capacitors will behave as a short circuit at higher frequency. Okay, so please consider this very, very carefully. And what about the stray capacitance? Now, stray capacitance value is in picofarad. And even if we go at very high frequencies, then also their XC value is a moderate value. It's neither too low or neither too high for open circuit. So that's why stray capacitors are neither short or open but are considered at higher frequencies. So this is the reason why in our analysis, the connected capacitors will behave as a short circuit and all the parasitic capacitances will remain in the circuit for analysis. Okay, any doubt in this? Anyone? Clear about this? Okay, so let me start building up the high frequency equivalent circuit in front of you all. So this is the circuit for reference. This is my circuit for reference which we have over here, right? We have a BJT. So first let me draw the diagram with BJT itself and later on we will replace the BJT with its high frequency model. Okay, so let me just draw BJT as it is. We will replace it by later on slightly. So let me draw first a BJT. Okay, BJT will have a emitter, will have a base, collector and emitter. Let me mark it over here. This is my base terminal, this is the collector and this is the emitter. Okay, now let's construct the circuit, the equivalent circuit. So over here also let me mark it. This is my base, that's my collector and this is the emitter. So over here from the base terminal, what all things I have over here, right? The coupling capacitors will be short circuited. The parasitic capacitance will be considered as it is. And over here we have a ground also. Let me add that ground. Okay, here it is. Ground is there. Yeah. So we'll keep keep the BJT part as it is. We'll try to put the remaining components into the circuit. So let's begin. Okay, sorry for this. Yeah. So let's continue. So from the emitter side, we have coupling bypass capacitor CE short circuited. So emitter will be connected to the ground. Then at the base and emitter, what do we have? R1 and R2 are connected in parallel. So let me draw it over here. R1 and R2 are connected in parallel. So we have over here R1 parallel to R2. You all also draw at your end. Then next we have is C mu, C pi. We have C mu connected between the base and the collector, and C pi connected between the emitter and the emitter and base. Emitter is grounded in here in the equivalent circuit, and between the base and the ground we have CWI, right? And then CC1 is short circuited. RSig is to be considered. So what do we have over here is C pi. I have to draw over here C pi value. Okay, this is in parallel. It's going to the ground. So I have a capacitor over here, which is C pi. And then I have one more capacitor over here, which is CWI. Okay, and here we have a resistor RSig along with the voltage source, which is Vs. Okay, so this much is completed. Now next is between the base and the collector I have C mu. So between the base and the collector I have C mu. So I'll draw the capacitor over here. Okay, so I have the C mu. Then from the collector side, from the collector to the ground, what do we have? So from the collector to the ground I have RC resistance, right? The DC supplies, DC's voltage supplies are grounded, short circuited. I have RC. Then I have a capacitor CCS, CWO. CC2 is short circuited, RL and V out. So let me draw that now on this side. On the collector side, first of all, I have RC. So this is my RC. Then I have CWO. CCS I can say. CCS, and I have another CWO. Winding capacitance, output winding capacitance. And then I have RL. This is RL, and finally I have output over here. Okay, so for this network, this is my circuit, which I have to replace the BJT also next with a hybrid PI model, right? Now, do you see any problem in this circuit? The problem in this circuit is this: C mu resistor, C mu capacitor. So why that is a problem? Because it is connecting my input part to the output part. So is there a solution to this problem? Is this an amplifier circuit? Yes. And one capacitor is connected between input and output. So how do we solve this problem? Anyone? Anyone with a solution? We have seen this situation before, right? We have an amplifier network and we have a feedback capacitor. But that feedback capacitor can be split up into the input and the output capacitances. So because analyzing such a circuit will be quite complex. So what is the next step? The next step is over here. Anyone? What do we apply? We apply the Miller theorem. Okay. So what do we write over here? Please write along. We'll Millerize C mu into CMI and CMO and replace BJT with its model, with its hybrid PI model, with its hybrid PI model. Can someone confirm if there is any problem in the audio or the screen is clearly visible? Please confirm.
Sir, the audio is clear and screen is visible.
Okay, thank you. And do it along with me, all these things, because this is important concept. Next, what I will do is I have to Millerize C mu into CMI and CMO. So what does this mean? It means application of Miller theorem. So this feedback capacitor, which was connecting input and output, is split up into two parts, CMI and CMO. So similarly here it will happen. Okay. Similarly here it will happen. And first of all, let me replace the BJT by its hybrid PI model. So let me do that right now. So first of all, I will draw the BJT hybrid PI model. So for this, I have my RPI over here. This is my base, this is my emitter, and over here I have my collector. Okay, let me write over here, this is base, collector, and emitter. Okay, between the collector, okay, sorry. I guess I have to turn off the, yeah. Let me turn off the ink to save. Yeah, let me continue here. So here I will have a current source, voltage controlled current source, which is GM into V pi. And I also have my output resistance of the BJT, and I mark it as RO. Fine. This is V pi. So this is my BJT. I mean my hybrid PI model of the BJT. Now, what will come onto the left? I mean from the base side, entire circuit will come as it is. This circuit will come as it is, right? Additionally, what will come? Let me add this. I mean you all have to draw it again, but I can add the circuit. Let me try it. Okay. So please draw it again from your side. I will be adding this part as it is. Okay, fine. So I will be adding it over here, but additionally there will be a capacitance which is in the form of CMI. Okay, this capacitance will be present, and that's the name is CMI. This is the input Miller capacitance, CMI. So now let me add that part which I have added earlier. Okay, I have to add it over here. Okay, fine. Let me add it. So y'all please draw it again no problem with that. At your end, you all draw it again. I have that facility available for me to copy that a part of a circuit, so I'm using that facility. Yeah, this is the part. Okay, and at the output side also same thing. I can add all this, but let me draw it once more. So here at the output at the collector side, I will have all this components RC, CCS, CWI, RL. But additionally, I have CMO. So let me first, and emitter is grounded basically. Emitter is grounded. Why emitter is grounded? Because the bypass capacitor is short circuited. Correct? So over here I have my capacitor CMO, output Miller capacitance. Okay, I can write over here CMO. And then what I have next is as it is, as I have done earlier, it will be like this will be RC followed by we have CWO followed by CCS. All the parasitic capacitance have to be considered, followed by RL. And finally, I have at the output terminal V out, plus minus V out. So this is my model over here. Let me just slightly, yeah. I hope it is entire model is visible on the screen. Correct? So this is my model.
Sir, can you reduce the size a bit?
Now?
Better, sir.
It's, yeah. This will fit the entire screen. Okay. So now what do we next is, basically what will happen is we can club, because all these capacitors are connected in parallel, right? On the input side and output side. So over here, this side, this part over here, this part is my input side, correct? From here to here is my input side of the circuit. And from here to here, I have my output side. I have my output side. So can I do one thing? I can club some certain terms together, right? So what I will do is I will be clubbing CWI, CPI and CMI. Okay, I'll be clubbing them together because they are in parallel. So capacitors in parallel will be like addition, right? Capacitors in parallel can be added, right? You all know this fact, right? So here I will be, yeah. So next I will be adding CMO, CWO and CCS. Okay. So my circuit will be becoming more compact now. Fine. So what I will do, what I'm writing over here, what I am doing over here. So what I will do, I will call one input capacitance CI, and that I will call it as, let me just slightly maximize. So this input capacitance CI will be parallel combination of CWO or CPI. Parallel combination, you can write it addition easily. I hope you all are aware of that. Plus CMI. Okay. Similarly, on the output side, what I can write? I can write CO, output capacitance will be, parasitic capacitance will be CWO plus CMO plus CCS. Okay. So what is CI and CO? This we call it as, CI we call it as input parasitic capacitance. All the combination of all the input parasitic capacitance. Okay, and CO is called as the output parasitic capacitance. Output parasitic capacitance. Now next step is to make a simplified form of the circuit over here. Correct? So let me just do it again. So I will cut this part of the circuit because I will be utilizing it. You all draw it again and in your books. So further I will simplify the circuit further now. Yeah, we have this much, right? At the input side, what do we have? At the input side, we have, let me add over here, uh, R1 parallel to R2 at the base side, correct? R1 parallel to R2. Then what do we have? We have R sig over here. Then we have Ci. We can write just one capacitor, Ci, input parasitic capacitances. And over here we have output, the input supply plus minus Vs. Fine, this is R sig. So now the input side has become very, very simple. At the output side, what do we have? At the output side, we have over here CO, output parasitic capacitance. And then we have two resistances which are in parallel, RC and RL. I can draw them separately also. And here we have the output. So please draw the circuit along with me over here. All these are grounds. Okay. This is RC, this is RL, and this is plus minus V out. Up till here, any problem in understanding? Anyone? Any doubt up till here? Because this is important step. So this circuit is called as high frequency equivalent circuit, small signal equivalent circuit. Okay, we have learned to draw three types of equivalent circuits. One is mid frequency equivalent circuit, one is low frequency equivalent circuit, and now this is high frequency small signal equivalent circuit. Everyone has understood? If you want me to write the name, I will write. This is called as high frequency small signal equivalent circuit of BJT amplifier. Okay, small signal equivalent circuit. Okay, fine. So further I have to analyze this network. Now I have to analyze this network. Earlier I have told you that this is my input side and this is my output side of the circuit, right? So similarly what I will do is next I will determine the higher cutoff frequency due to input side. This is my input side, base emitter side is input and collector emitter side is output. Okay, so I'll consider on the basis of, now I'll analyze further on the basis of input and output side. Is this clear? Because the Ci capacitor is different and Co capacitor is different. They are not the same. Even the resistances are different. So basically what I will do is I will be finding, let me just write it over here, what I will be doing over here. Next will be, I will be concentrating on finding the higher cutoff frequency due to the input side of the circuit, and then next output side of the circuit. Okay, so let me find out next. I will write over here, estimate the higher cutoff frequency, estimate the higher cutoff frequency for the input side, for the input side circuit. Okay, so we'll estimate higher cutoff frequency for the input side of the circuit. That means we have to find FHI. We call this as FHI. Okay, so why do we, while we consider this, when we consider this, we'll consider Ci alone. We'll consider Ci alone. So for this, what do we do? consider CI alone. You remember how did we do low frequency analysis? We considered one capacitor at a time and then we analyzed the remaining one. I mean, we have considered one capacitor at a time. Remaining capacitors were short circuited. Okay. So while considering CI, what we will do? We'll short circuit CO and input supply VS. Are you all following what is going on over here? I mean, the trend. Any doubt in understanding this part? Now let me copy this entire circuit again because I'll be requiring it now in the next step. Okay. So what I will do is I'll add the entire circuit again over here, and then I'll be applying this concept and finding out the FHI. Right. So this was my circuit over here. Let me remove this part. Okay, fine. So what we have to do over here? We have to short circuit CO. So CO part will be gone. So short circuit means I will use a red color. Okay, this is CO is short circuited as well as VS source is short circuited. Huh. Now we have to analyze the circuit. Now tell me now how to do it. Anyone? See, if I short circuit this RO becomes redundant, RC becomes redundant, RL becomes redundant. And what is the impedance offered by the current source? Anyone? Impedance offered by the current source is infinite or zero? Hello? Can anyone tell me? Whether the impedance offered by the current source will be infinite or zero? Current source, remember. It will be infinite. So therefore, your current source will be considered as an open circuit. Okay, so we have left out with only this part of the circuit over here, this one. So let me redraw it one more time. So we have over here R sig. Okay, let me use the black color. We have R sig, then we have CI, then we have R1 parallel to R2, and then we have R pi, right? This part will be open circuited. This part will be open circuited. This is R pi, this is R1 parallel to R2, this is ground, this will be ground, and this also is short circuited. So this is R sig. Now, how to calculate FHI? How to calculate FHI? Over here. What will be R equivalent? Anyone? What will be R equivalent for this network? Oh, sorry. What will be R equivalent for this network? Remember, this is similar to this circuit now. I have my signal applied over here. I mean, let me redraw it again. Correct. And this was the circuit. And then I have a system. This is my system. And this we apply the input. Basically here we are not considering the input for finding R equivalent, but in total this is how the system looks like. If this is R1 and C1. So anyone can tell me what will be the formula and the frequency response plot for this circuit? The frequency response plot will be like this, right? Correct? We have analyzed this circuit in lecture number 2. You could remember, recollect. So here we have a higher cutoff frequency. So let's say this is F naught, this is F and this is AV. Let's say we have such kind of a response. Okay. So what will be F naught given by? F naught will be given by 1 upon 2 pi R1 into C1. So in our case also we have a system, right? So this is a system. Sorry for that. Yeah, that is a system. So for this system we have to find out Ri. So anyone can tell me what is Ri? Anyone? Quickly tell me what is Ri. Ri will be R1 parallel to R2 parallel to R pi. So R1 is Ri is R1 parallel to R2 parallel to R pi. Now next tell me what will be R equivalent, the equivalent resistance. Because ultimately we have to find FHI, right? So R equivalent is what? Come on. Whether it is R6 parallel to Ri or R6 plus Ri. Tell me this. I give you two options now. Someone please reply. Because FHI will be 1 upon 2 pi R equivalent into CI. So that's the value of FHI. So that's why we are calculating R equivalent. Now please tell me, someone. I hope that I am audible still. So please respond and tell me what will be R equivalent. Whether it's R6 plus Ri or R6 parallel to Ri. Quickly, please tell me. Is my internet connection working? No one is. Yeah, please respond. What is R equivalent? R equivalent will be R6 parallel to Ri. Remember, over here it's not connected in series, it's connected in parallel. Your R6 is parallel to Ri, right? So that's mistake which students do more often. So R equivalent in a high frequency equivalent circuit, it's R6 parallel to Ri. So now this is the formula for FHI, okay? And that's how you determine your higher cutoff frequency for the input side. And for this, what is CI value? What is the value of CI over here? Where CI is equal to C pi plus CWI plus CMI. Now anyone can tell me what is CMI? Input Miller capacitance, what's the value of it? Let me go back to the circuit. Over here, what is CM? What did we replace? We replaced C mu, right? So what is the formula? CF into, what is the formula for Miller capacitance, input capacitance? 1 minus AV into C mu, correct? So that is what we will write over here. I hope you all are following. Okay, so CMI will be C mu into 1 minus AV, the voltage gain. Fine. So this is how we determine the value of FHI. Any problem in understanding this part, please let me know before I proceed ahead. Any problem in understanding this? This I should written as Ri. Yeah, now it's fine. Okay. So if this is clear, then the Ri part will be, we have to determine similarly estimate the higher cutoff frequency for the output side circuit, right? So let me redraw this. Let me cut and you might have to redraw it one more time in your books. Okay, fine. Let me add that part over here. Next, we'll find FHO, the higher cutoff frequency due to output side circuit. Because there are only two capacitors present, Ci and Co. So we'll estimate Here, let me do some changes. This is fourth part. And here we are estimating the higher cutoff frequency for the output side circuit. So we are doing it for the, okay, output side circuit. So that means we are determining FHO. We are determining FHO. Okay. So for that FHO, what do we do? We'll have to consider CO, and we have to short circuit CI and VS, right? So we'll do that. Here we have to short circuit CI, and we have to consider CO. So let's do that. Let me take the circuit up slightly. Yeah. So I will put back the value of CO and I have to short circuit CI. So CI part is short circuited now. It's taking slightly time, so please bear. This is grounded now, short circuited. And CI have to consider as it is, CO. So CO will be present in the circuit. Correct? And now again, we can do it very easily. If this is a short, the R1, R2 resistance becomes redundant. Even the R pi value of resistance become redundant. Okay, because this is a short. Correct? So base emitter side is entirely gone, short circuited. And what about this current source? It's again an open circuit. Why? Because the impedance offered by the current source is infinite. And then we have left out with this network over here, right? So let me draw that again for your reference. So now we have RO over here. Then in parallel to we have a capacitor, CO, right? Let me draw CO on that side a little. This is parallel, right? So I can push the RC and RL on that side, right? So let me do that. Okay, fine. Let me add RL now. This is RC. Let's say I will add RC over here, and then I have a capacitor. Then I have RL. This is CO, right? Okay. So this is the circuit now. Do you have the output over here? Because this part is gone. Na? This is over here open circuited, right? So that part is gone. Left hand side is gone. This is my V out. So now we have to determine FHO. So how do we do that? Again, the same concept will come. I'll draw the equivalent circuit over here. So my equivalent circuit will look something like this. Let's say that I have my resistance R1 over here. This is my capacitor, and I'm finding the equivalent. I mean, in this case, it is this way. Sorry for that. Correct? Over here it is. This is my V out. I mean, let's consider this as V in. This is R1, C1, and that is my system over here, which I've drawn. So for this system, I have to calculate RO. RO. Let me write it as V out. So for this system, I have to calculate RO, right? So let me draw the system over here. So this is my system. So for here, I have to calculate RO. So can anyone tell me what is RO from the network? What's the value of RO? RO will be RC parallel to small RO, correct? RO will be, capital RO will be RC, capital RC parallel to small RO. Now, anyone can tell me what will be R equivalent? R equivalent. So R equivalent will be capital RO parallel to RL, not plus, it's parallel to RL. Why it's in parallel? Because they're connected in parallel, right? R equivalent will be RO parallel to RL. And next, what will be FHO? higher cutoff frequency due to output circuit will be 1 divided by 2 pi into R equivalent into CO. Correct? So that's the formula. That is the formula for higher cutoff frequency due to the output side circuit. And whereas your CO value will be given by CMO plus CWO plus CCS, where the output Miller capacitance will be given by the feedback capacitor C mu into 1 minus 1 upon AV. So please note it down, these things. Please note down this. I'm writing it live so that you all can also mention the value over here. Okay? Any doubt in understanding this part? How did we get this? Again, the frequency response, you all know how it will be. The frequency response will be something like this. So it's the higher cutoff frequency which we are interested in this case. So this is your AV and this is your frequency is the higher cutoff frequency. So basically this will become my FHO, okay, whose formula will be given by 1 upon 2 pi, expression will be given by 1 upon 2 pi R equivalent into CO, where R equivalent is RO parallel to capital RO parallel to capital RL, and CO is this over here, okay. Clear about this? So this was the point number 4. Last is, at the last, what we need to determine. Fifth step is estimation of FH. Estimation of FH. So how do we do that? Remember FH, sorry. This will be FH. Estimation of higher cutoff frequency. Now we have two cutoff frequency in the circuit, higher cutoff frequency. So you have to select, I'll write over here, select FH is equal to minimum of. So you have to select minimum of FHI, comma, FHO. So whichever is the minimum value among FHI and FHO, that you consider as the higher cutoff frequency of the BJT amplifier. Okay. So this is the statement. I mean, this is the concept which you all have to remember. Many people get confused between higher and lower cutoff frequency. For lower cutoff frequency, it was maximum. For higher cutoff frequency is the minimum among FHI and FHO. So please note down this. This is the higher cutoff frequency, higher cutoff frequency of amplifier. Higher cutoff frequency of amplifier. Okay, and that completes the high frequency response analysis. So this will complete the high frequency response analysis, right? And if they tell you to plot the, let's say if they tell you to plot the high frequency response, okay, together with the low frequency response, how will you plot? They will tell you to plot the frequency response of the circuit now. They are asking you to find out FH and FL, and they are asking you to plot the frequency response. So how will you plot the frequency response? Very simple it is. I'll mark the X and Y axis, just a minute. Yeah. So let me take this Y axis, X axis, this is frequency, this is my gain in dB, AV, and my frequency plot will look something like this. Okay. If you go 3 dB down the maximum frequency, I mean the maximum gain, you can mark over here, this will be my FL and this will be my FH. So if they tell you to plot the frequency response, this is how it will look like. This will be my AV mid. This is the maximum value. And you go down over here like this. Okay? 3 dB down. So this is 3 dB down. Understood? So this is how you will conclude your high and low cutoff frequency of a BJT amplifier. In fact, we have also discussed the mid frequency response, right? Where the gain was remaining constant. So this completes this topic, this concept. Any doubts, anyone, in this? Anyone having any doubt, any query? Any step not clear? Please let me know. Everything is clear, how to draw the equivalent circuit and how to determine the formula. See, the formulas will not remain the same every time. It will keep on changing as per the circuit given to us. Okay. So next we'll move on to a numerical quickly. We have solved that numerical before. So one last learning step from here is that now that we have seen the entire analysis of the circuit, sorry for that. One last learning step I forgot to tell you all, that while determining the higher cutoff frequency, you saw that over here it was affecting the higher cutoff frequency only, the graph in the plots, FHI and FHO. So that's why, and this fall in the gain is only due to the parasitic capacitance. You remember we started the lecture saying that the gain of the amplifier fall at higher frequency is due to, here it is. Why does the gain of the amplifier, fall at higher frequency? They fall due to the parasitic or inter-electrode or stray capacitors in the form of C mu, C pi, CCS, CWI, and CWO. And the gain fall at low frequency due to externally connected capacitors, CC1, CC2, and CE. So here we can additionally write over here, the cutoff frequencies are FHI and FHO. For low frequency response, they were FLCC1, FLCC2, and FLCE for BJT amplifier, right? And these capacitors, connected capacitors, were the culprit for falling of gain at low frequency, and over here the parasitic capacitance are the culprit for falling of gain at a higher frequency. So that's the learning from this high frequency response of BJT amplifier. Okay, now let's quickly move on to numerical. So what I will do is, we have solved this numerical before. I will explain. Can anyone confirm, is this new whiteboard visible to you? I have opened a different one. Anyone can quickly confirm?
Yes, sir.
Yeah.
Okay. Yeah. So if you remember, this circuit we have solved in lecture number 6. I think lecture number 5. Correct? Same circuit. But additionally, and we have got all the answers. We got the value of lower cutoff frequency and the voltage gain in dB. For the same numerical, if they additionally give you this data, that C pi value is 36 picofarad, C mu value is 4 picofarad, CCB is same as CCS. Okay, don't forget that. CCB is 1 picofarad, output wiring capacitance is 6 picofarad, and CWI is 8 picofarad. So we have to additionally find the higher cutoff frequency FH and plot the complete frequency response. Okay, so if they ask such a numerical, your steps will remain the same. I am just going through the steps. So we have already covered this numerical before. So with the DC analysis, you calculate ICQ. From the small signal parameters, you calculate R pi and GM. Then you calculated FL of CC1, FL of CC2, and FL of CE. We have seen all that before. I'm not going to discuss that again. So among that, we got the lower cutoff frequency. I'm just moving ahead now. Yeah, we got the lower cutoff frequency as 316.81 hertz, right? And then next was we calculated AV mid. So AV mid was coming out to be, how much it was? 49.56 in magnitude, but in dB it was 33.9, right? And we also plotted, you remember, we also plotted the low frequency response. So let me show it to you, the low frequency response also. Yeah, this is the low frequency response. So now with the given data given to us, we'll additionally calculate the FH and we'll plot the frequency response again, the complete frequency response. So let's start our numerical. Let me write step number 10. Okay. So since we have fresh in our minds how to calculate FH1 and FH2, and it's the same numerical, so we'll write over here calculation of FHI. So in the exam, you can draw the circuit or you can directly write it. It's better to draw the circuit, I mean the equivalent circuit once, so that you have the clarity what is going on and if nothing is missed out. But since it was the same circuit which we have just now analyzed, I can directly write the value of FHI. Okay, formula also directly, because just few minutes ago we have discussed this and it's the same circuit. So FHI formula is given by 1 upon 2 pi R equivalent into CI. Okay, where R equivalent is given by, R equivalent is R sig parallel to R1 parallel to R2 parallel to R pi. I will give you all the values, don't worry, it's the same numerical. And then we have to calculate CI also. So CI is basically CMI plus CWI plus C pi value, right? Let me check. Yeah, C pi. Okay. So what are the values given to us? The value of R sig is 1 kilo ohms. This is 1 kilo ohm. R1 parallel to R2, we have calculated it as 8 kilo ohm in the numerical. And R pi value is 1.655 kilo ohms. So if you can calculate the value of R equivalent and let me know. Till then, I will write the other formulas. So R equivalent equal to how much kilo ohm? You let me know. Okay, if you have your calculator right now with you, calculate this, put this tree, okay, the parallel combination of these three. So you should get close to 578 ohms. Roughly you should get 578.29 ohms. Please, one of you confirm the answer if you have already got. R equivalent will be 578.29 ohms. Please confirm this. Now, here CMI we have to calculate. So CMI will be C mu into 1 minus AV. Okay, what is C mu value given to us? C mu value was 4 picofarad. Okay, and how much was AV? AV was minus 49.56. Remember, we have to consider minus sign only. Huh? We have to consider minus sign only. So it will be, can you calculate this? 4 pico into 1 minus of minus 49.56. So this will become 202.24 picofarad. Please note this answers down if you have not calculated yet. Please calculate them. I'll encourage them to calculate them along with me. So CMI value is coming out to be 202.24 picofarad. CWI value is given to us. It's, I guess, CWI is 6 picofarad given. And C pi value is 36 picofarad given to us. So now calculate, please calculate CI. Calculate CI value. You should get close to, answer is close to, let me cross check, 244. 244.24 picofarad. Please confirm the numbers. If you are getting anything different than this, please let me know immediately. So now that we know R equivalent and CI, we can easily calculate FHI. So FHI will be 1 divided by 2 pi into R equivalent, which is 578.29 into CI, which is 244.24 picofarad. Picofarad is 10 raised to minus 12. So please calculate this FHI. How much is the answer? Let me know. So FHI after calculation, it will come to 1.127 megahertz. 1.127 megahertz. Please cross check this value. Students, please cross check this value quickly. We have 3 minutes left, so I will proceed ahead now. You can cross check this value later. Okay. Next, I'll go to step number 11. Let me quickly complete the numerical. You can verify the answers. So next is calculation of okay, it is stuck slightly. Just give me a sec. Next is calculation of FHO. So calculation of FHO will be, we know the formula now. We have just now a few moments ago we have discussed. Is the same circuit, BJT amplifier. It is 1 upon 2 pi R equivalent into CO. Okay. Now we have to find R equivalent quickly. So I am just writing it down, the values. You can calculate it later. So R equivalent is RC parallel to RL. Okay, RO was not given, so RC parallel to RL, and this comes out to be 1.419K. You can cross check the answers later. Over here, RC value was 4K and RL value was 2.2K. Okay. Next is CO. Next we have to calculate CO. So CO was CMO plus CWO plus CCB. Okay. So here we have to calculate CMO, which is given by C mu into 1 minus 1 upon AV. Okay. And your CWO value is also given to you. Let me check how much was the CWO value. So CMO value, if you calculate, this is 4 picofarad. This is AV value is minus 49.56. So CMO will come close to, CMO is coming close to 4.04. 4.04. I told you this, it will come close to the feedback resistor value only. So that's what we are getting. Then CWO value. What is CWO value? CWO value is 8 picofarad. CWO is 8 picofarad given to us. And CCB value is how much? It's given 1 picofarad. Okay. So please calculate CO now. So CO will be equal to 4 picofarad plus 8 plus 1. So that will be 13.04 picofarad. Okay. That's the value of CO. So next we quickly calculate FHO. So your FHO will be 1 divided by 2 pi R equivalent into CO, which will be, I can write down directly the answers over here. R equivalent value is how much? 1.42K into 13.04 pico. So if you calculate it, you will get it FHO as 8. Let me write it down over here. So if you calculate this, you will get FHO as equal to 8.6 megahertz. If I am not mistaken, please cross check it. FHO value will be 8.6 megahertz. So we have calculated FHO and FHI. Now next step is we have to quickly calculate FH, total FH, right? So this was 11. So last step. One last step is remaining. Calculation of those who are, it's 2:15, beyond 2:15. So please, those who are next lecture is started. Let me record the meeting. You all can leave the meeting till then. I will record your attendance. Don't worry. Okay, let me complete the numerical first. So next is calculation of FH. Okay, just a minute more. That's it. So calculation of FH In calculation of FH, what do we do? FH will be minimum of FHI and FHO. So remember FHI value was how much? 1.127 megahertz. So your FH will be equal to 1.127 megahertz because it's the lower among the 8.6. 8.6 is the higher value. So we have to select the lower value of FH. So this is my high cutoff frequency, high cutoff frequency of the amplifier. This is my high cutoff frequency of the amplifier. Okay, and if you want to plot the frequency response, it's quite simple. It will be very easy. So I already told you all that how to do that. You all can do it on your own. But let me draw one last frequency response plot over here. So this is called as complete frequency response. This is called as complete frequency response. Okay. Let me go slightly down. Yeah. So how it will look like? It will look something like this. Y-axis, x-axis is the frequency, y-axis is the voltage gain, and a plot looks something like this. Okay. We mark the higher take it. Let me redraw the graph. The pen sometimes are not working, so it's fine. Yeah, you have to mark the higher midband gain, which is the highest value over here. Okay, I guess I have to take it a little down. Here it is. Okay, and then you go 3 dB down over here and over here also. And here you will mark FL and here you mark FH. Okay, and if you want to write the cutoff frequency, what was the cutoff frequency FL? We found out in the numerical was 316, close to 316 hertz, and the higher cutoff frequency was 1.127 megahertz. And how much was this value? The highest value was 33.9 dB, and that was the voltage gain. And this was 3 dB down. Okay, this was 3 dB down. Okay, so this completes the numerical on finding the, and if someone finds you the someone tells you to find the bandwidth, how to find the bandwidth over here? So bandwidth will be FH minus FL. So that will be approximately equal to FH itself, because FL value is very small. Okay, so if they tell you to calculate the bandwidth, you can calculate it like this. And if they tell you to draw the complete frequency response, you have to do it like this. Sometimes they tell you to draw it on the semi-log paper. Okay, so semi-log paper, you all are doing it in LT Spice. X-axis will be in semi-log, Y-axis will be in dB, normal linear axis. Okay, so yeah, that's it for this lecture. If you have a query, please do ask. It was the same numerical. Only thing is we have found out the higher cutoff frequency, and we have drawn the entire complete frequency response of the circuit. Okay. So with this, we complete the high frequency response and the low frequency response of BJT amplifier. Next time, we will start with the high frequency model of a MOSFET. Fine. So yeah, thank you for joining and sorry for taking your 5 minutes.